so we are recording. So we're going to talk about matrix factorizations, in particular the LU factorization. Okay, so let me give you a moment to copy this. And all right, this example. Okay, so what's going on here? Matrix factorizations, what are those? Okay, well, for this problem, I want you to take it on faith that the matrix A can be factored as the product of these two matrices. Now, I want to mention matrix factorization, LU factorization, doesn't have to be for a square matrix. It could be for a non-square matrix. Okay, but I mean, look at these. Look at these. Look at this. Look at these matrices here. So this matrix is matrix L. This matrix is matrix U. Okay, so I mean, what do you think that L stands for? You know, I mean, look at matrix A. Good, that's right. L stands for lower. And if you look at the matrix L here, above, where are the non-zero entries? They're all below the diagonal. But above that, I mean, you have a diagonal here. Let me be more clear here. Hold on. One moment here. You have a matrix L, you have a matrix U, and you have a diagonal here on L consisting of ones, and the entries are the non-zero entries above or below the diagonal for that matrix L. Are they above or below the diagonal for matrix L? They're below. That's right. Above the diagonal of ones, good name, a good, hold on here. Hold on, class, one moment. Let me get the chat back here, one moment. And, well, thank you. I know Naima responded, and I'm trying to think who else responded. I can't find it on my little thing here for the chat here. You have to learn how to do that. But at any rate, thank you. So yes, on matrix L, below the diagonal of ones, you have non-zero entries. And above the diagonal, you have entries of zeros. So this is called a lower, this matrix L is known as a lower triangular matrix. And in fact, it's a lower unit triangular matrix because you have ones along the diagonal. Now look at matrix U. Look at matrix U. Here's the diagonal. And are the non-zero entries above or below that diagonal on the matrix U? The non-zero entries, good name, are above. They're above. And so what does U stand for? L stands for lower. U stands for upper. That's right. That's right. Good, Nema. So because the non-zero entries are above the diagonal. So we can express matrices in this, what's called LU factorization. Now, the question is why would we be interested in doing that? Well, you're going to find that we can use LU factorization to easily solve a system of equations. And what we're going to do is we're going to use this LU factorization to solve the system of equations AX equals B, where the vector B is given by -7, 5, and 2. So I'm introducing section 2.5 today. We're going to cover that. We're going to cover more of 2.5 and on Wednesday. Also on Wednesday, we're going to be talking about computer graphics, section 2.7 as well. So it'll be I hope all classes are exciting, but Wednesday will be very exciting. Okay, so how does this LU factorization work? Okay, how does this work? So this is another way that we can solve a system of equations. Okay, let me show you. May I move to the next page? Okay, Benjamin's good. Name is good. Okay. All right. So first of all, we represent our system of equations as a matrix equation, A times the vector X equals B. But now if we can represent the matrix A as L times U, we can write that matrix equation as L times U times X equals B. No problem there. But look at what we can do. Matrix multiplication is associative. So I can choose to multiply the matrix L times the matrix U first and then by the matrix X. Or I could similarly, well, I guess what I'm trying to say is instead of going L times U and then times the vector X, I could find out what U times X is and left multiply by the matrix L. Matrix multiplication is associative, so this way of expressing the matrix equation is okay. And what we're going to do now is we're going to let the vector y equal U times X. We're going to let the vector y equal U times X. Okay, and if we do that, then L times the vector y would have to equal the vector b based off of this representation of the matrix equation. So essentially what we have is by making the substitution, by letting the vector y equal the matrix U times the vector X, we can then have another system of equations, the matrix L times a vector y equals B. I mean, it follows. It follows. If y equals U times X, then L times y equals B. What we want to do is we want to solve this system of equations, augmented system, for the vector y. So what I do is I have my augmented matrix here. This here is my system of equations represented with the lower unit triangular matrix L and the vector B. And I want to break that system down. I want to solve that system. Okay. So do you think it's going to be easy to solve this system of equations? This augmented matrix, is it going to be easy to solve it for the vector y? Okay, why? Why is it going to be easy? I'm seeing a lot of yeses. What makes it easy? Good. Benjamin, Naaman, Eleanor. Good. What intuitively then? Why do you think it's going to be easy? What's making it easy? Okay, Hung says the numbers. Okay. Namus says it's reduced. So you're all saying what's in the augmented matrix? What are you seeing more of that you're kind of maybe not used to seeing? You're seeing, what number are you seeing a lot of? Good, zeros. You're seeing zeros. Good, Hung. Good, Eleanor. Good, Naaman. So, all right. So, of course, what we want to do is get this augmented matrix here in reduced row echelon form. So all we need to do is get pivots. Well, let's get pivots where the -1 and the 2 are. So of course, I'm going to take 1 times the first row, add it to the second row, place the result in the second row. Okay, easy. And then I'm going to take 2 times the first row, -2 times the first row, I should say, add it to the third row, and place the result in the third row. Very easy to do. And of course, look, all we have now is one more pivot, the -5. Okay, no problem. We'll take 5 times the second row, add it to the third row, and replace the third row by that result. And there we have it. The augmented matrix is in reduced echelon form. And that was easy to do. Very few row operations. Incidentally, what's the value now for y1? What's the value for y2? And what's the value for y3? Good. Y1 equal good. Good. Y1 equals -7. Y2 equals -2. And Y3 equals 6. Okay, and so we have found, we've solved this here, this intermediary system, we've solved it for the variable y. Now what are we going to do? The variables, the y variables. What are we going to do with the y vector now? Well, we're gonna use that to solve this system of equations here, because that's the one we're interested in, because that has the original variable x in it. Okay, so that's the one we're interested in solving. So to that end, let's move on here. Here's our vector y, and now we're going to solve u times x equals y. So here's our augmented matrix. Get that a little bit further away here. I don't want that so close. Well, hold on, class. There we go. That's okay. All right. Here's our new augmented matrix, and we're going to solve for the x variables. Are we happy? Are we happy with that augmented matrix? Do we like that augmented matrix? Should it be easy to solve for the x variables? Okay, why, Nema? Nema says yes. Why? What number do you see a lot of in this augmented matrix here? Zeros. Good, Abby. Got 3 zeros here. As a matter of fact, this augmented matrix is already in what form? Yeah, well, yeah, Nema, the zeros are lower, but yeah, that's already in what form? That augmented matrix begins with an E. It's in echelon form. Good. All right. So, all we have to do is the backward phase. Okay. So let me do this kind of quickly, because I know our. So of course, I want to get pivots here and here. I want to get zeros there. So I'm going to take the third row, the -1. I'm sorry, the third row, I'm going to multiply by -1. Add to the second row. Put the result in the second row. This shouldn't take more than 5 minutes here to finish this example out. So if you could stay a little bit, I'd appreciate it. If you have to go, I understand. But if you can stay, it'd be nice. Let me just make sure here I'm doing this right. let me see, hold on. I think I copied the matrix down. I think this is just the matrix. No, 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 that isn't right. I made this -1 a +1. So I took the third row, multiplied it by -1, and replaced the result in the third row. Okay, and then I want to get zeros in those two spots, so I'll use this 1 as a pivot. Okay, and so what I'll do is I'll take 1 times the third row, add it to the second row. So I'm taking I'm adding the second and third equations together. Put the result in the second row. Yep, that's right. And then I'm going to take 2 times the third row, add that to the first row, put the result in the first row. Right. And now what I want to do is I want this number here to be a 1. So I'm going to take the second row and multiply it by -1/2. And put that result, replace the second row with that result. So we're almost there. We almost have this in reduced echelon form. All we have to do now is get a 0 where that -7 is, and I'll use this 1 as a pivot. Okay, so may I go to the next page? Are there any questions? Is everybody okay in terms of copying? Okay, maybe give me a thumbs up when you're ready. Okay, Andres is ready. Name is ready. Okay, good. Let's move on then. Thank you. All right, so what I did then was, let me see, let me go back here. I'm going to have to take 7 times the second row and add it to the first row. So that's what I did. I took 7 times the second row and added it to the first row and replaced the first row with that result. And then finally, I want this 3 to be a 1. So I'll take the first row and multiply that by a third and replace the first row with that result. And now it's clear what x1, x2, x3 are. And I've solved for x1 equals 3, x2 equals 4, and x3 equals -6. So we've used, and this is using the LU factorization procedure for solving a system of equations. And the LU factorization is a more efficient method for solving a system of equations than using an inverse to solve a system of equations. So they have a numerical note at the end of section 2.5 that talks about that. Perhaps we'll lead off on Wednesday's class with that numerical note. But of course, one thing that might come to your mind is, okay, this is great. You gave me the LU factorization. You gave us the LU factorization of the matrix A. But suppose I need to find the LU factorization of the matrix A. I mean, that's Of course, that's an important thing to be able to do, right? So I'm going to show you how to do an LU factorization of a matrix A in Wednesday's class. But are there any questions with with what you just learned today from section 2.5, LU factorization? Okay, well, on that note, I'll stop the recording.